Thank you very much, Oliver, for introducing me so nicely. Thank you very much for coming, of course, and for your interest in the topic that I'm going to talk about. And of course, I would like to thank Honeywell for having me here today. It's a pleasure and honor. And of course, well, the main task of such a lecture is to inspire you. And that's what I'm going to try to do. I will tell you a bit about my science, but also about my personal trajectory. And of course, there will be ample time to ask questions about anything you want. So I'm sure you're familiar with the saying, "A picture's worth 1,000 words. Seeing is believing," and this applies, of course, to our daily lives, but not only there. It also applies to sciences. And if you look back in history of the natural sciences, especially of the life sciences, you will find that the beginning of the natural sciences as we know them today very much coincides with the invention of the light microscope. Because with light microscopy, mankind was able to see for the first time that every human being consists of cells as the basic units of structure and function. And of course, many discoveries were made with a light microscope, such as bacteria and diseases as a result of discovering the bacteria, such as tuberculosis and so on. But I'm sure you will remember your school days, because in your school days you learned that the resolution of a light microscope is fundamentally limited to about half the wavelengths of light. So that amounts to about fifths of a thousandth of a millimeter, so 200 nanometers roughly. And if you want to see smaller structures, smaller details, you have to resort to electron microscopy. Now, electron microscopy, which was invented actually in the mid of the 20th century, attained a much higher spatial resolution, and as a result, viruses were discovered, important protein complexes, and you get down in electron microscope to a spatial resolution that is at the atomic scale or subatomic scale by now, and that's done routinely. And so you may ask, why are we still interested in the light microscope now that we have the resolution of an electron microscope? Especially if you are a physicist like me, you would say, okay, the light microscope is, of course, the totally outdated technology that was invented in the 18th or 17th century. Now, the answer to that question is actually given in the next slide. I made a little experiment, being a physicist, so experimental physicists like to do experiments. So I went to the library and I picked this journal, which is one of the journals, or more, say, respected journals in basic medicine. And so I checked out the numbers of papers reporting important basic medicine discoveries, the number of papers that used an electron microscope or the rest of it, like scanning probe microscopes and so on, and those papers that used a light microscope. Now you see which of the two won. So clearly light microscopy wins, and this is really representative. So in other words, if a biologist checks out a cell or something, in 80% of the cases, he or she will use a light microscope, and for very good reasons. The first reason is that light microscopy is the only way to look into the interior of a living cell. You cannot do that with an electron microscope because an electron microscope requires evacuation. You have to take the air out. And this doesn't work for living cells because it's not compatible with aqueous conditions. So no way to do that with a living cell. And you can't put a living cell into a vacuum. Now, that's one reason. But there's another reason which is as important as the compatibility with living cells. We know by now that there is, of course, a nucleus in a cell and mitochondria and so on. You may have heard of them. But what we do not know about the distribution of the 10,000s of proteins, different proteins in a cell, nucleic acids and so on. And it's very difficult to find out what a certain protein species actually does in a cell. Why is it difficult? It's because if you want to see a certain protein species, you have to make it distinct from the rest, from the other, say, 10,000 of different types of proteins. And to light and to electrons, all these proteins look the same. But in light microscopy, we have a very nice option to make those proteins of interest distinct, to highlight them. Namely, we can attach a fluorescent molecule to the protein of interest, and this fluorescent molecule has a very simple feature. It's usually an organic molecule that has a basic energy ground state and a basic energy excited state, and it fluoresces, meaning that if we shine green light on it, for example, it could also be blue light, of course, but let's assume it's green light, a green photon will be absorbed by the molecule will be raised to a higher lying state in here, so the molecule is going to be excited, and then after a brief period, about a nanosecond or so, the molecule comes down by emitting a fluorescent photon. Now, the fluorescent photon has a different wavelength as the light with which we illuminate the molecule. So this is green, you see, and now the fluorescence is yellow. And because the fluorescence is yellow, it's very easy to distinguish the fluorescence, the light that comes out from the light that goes in, and by the wavelengths. And that's why fluorescence microscopy is extremely sensitive. You can use a filter, okay, a color filter, and then you will see only the fluorescent light, and you don't have to worry about any stray light produced from the illumination light. As a matter of fact, fluorescence microscopy is so sensitive that you can detect a single molecule. I really mean a single molecule in a cell, in a living cell. You can still see a single molecule. However, don't forget, if there is a second molecule coming very close to the first molecule, closer than the resolution barrier of the light microscope, closer than the 200 nanometers, it will not be possible for the microscope to tell them apart. So if you look in the microscope with 2 or 3 molecules being very close to each other, then they will appear as a single molecule, more or less, as a single blurred entity. So resolution must not be confused with sensitivity. So fluorescence microscopy is as sensitive as it gets, single molecule. But its ability to tell features apart is still limited, or was limited. And so it was clear that if one manages to overcome this barrier here, and if one managed to produce a light microscope that can tell features apart that are closer than this distance, it would really have a major impact in the life sciences, because you could look into the cell and see details that you couldn't see before. Now, I'm explaining to you where this resolution barrier actually comes from. So this, say, 200 nanometer resolution barrier. There are many ways of explaining it, but the simplest one is also the most profound one. And of course, physicists want to boil down things to, or a problem down to the most basic elements. Well, in simple terms, you can say that the most important element of a light microscope is the objective lens. And the objective lens is nothing but an expensive or complicated lens system that boils down to a single lens, a very good single lens. And so the role of a lens, as you will appreciate, is to focus the light down to a point. And you know, of course, that light propagates as a wave, and because of this wave nature of light, it will not be possible for the lens to concentrate the light on a single geometric focal point. So I'm showing this point here, this green point. It will not be possible for the lens to concentrate the light on a single geometrical point because of this wave nature, because of diffraction. And so what we get here is a minimum spot of light, which is defined by the wavelengths, by the phenomenon of diffraction, that has a finite size. It is at least about half a wavelength in this direction and about a wavelength in that direction. And this is why we have the 200 nanometers near and about the 500 nanometers in this direction for visible light. Now, this inability of the lens to focus down the light to a point has a major consequence. Now, if we're having a sample in here and say many molecules, as you see the molecules in here, of course, they will be flooded with the green light simultaneously, no way out, because we have this big spot. And so all the molecules that are in here, let's assume these are now fluorescent molecules, they will be flooded at the same time with this light, and as a result, produce light simultaneously at the detector. So if you place the detector in here to collect the light that is produced here by the lens, then you can imagine that each of the molecules, of course, will produce light. It will be focused in here, very clear. It has to be focused. And because of focusing, each of the molecules will produce this blob of light again, this time in a detection plane. And then the next one will do the same, and the next one will do the same, and the same again, same again. And in the end, of course, there will be many blobs of light that have a finite size because it's focused. And because they are so close, you will not be able to tell the single from the molecules apart, because they're simply overlapping, they're overlapping in space. And so if you place the detector in here, it could be a photomultiplier, could be the eye, or even a pixelated detector such as a camera, no detector will be able to tell the signal from those molecules apart. It will be confused by the detector, completely confounded. And so it was clear that you cannot separate features that are closer together than this blob of light, because the signal that is produced by them will be confused by any detector that is imaginable. Now, the man actually who realized this problem lived at the end of the 19th century. In Germany, in Jena, to be precise, is this man Ernst Abbe, and he formulated this equation which is named after him. It's basically saying that in order to be separable in a light microscope, two features, molecules, whatever, have to be apart at least by this number here, given by the wavelengths, lambda, divided by twice the so-called numerical aperture of the objective lens. So this is twice the sine of this half angle here. This is a number like 2 or 3. Wavelength is something like 4, 5, 600, and so you end up with the 200 nanometers. And this equation, of course, you will find in any physics textbook, of course in optics textbooks, but also in life science textbooks, simply because microscopy is so important to the life sciences. Not only there, you will also find it on a memorial which was erected in honor of Ernst Abbe in Jena, in Germany, where he lived and worked. And on this memorial, you will find this equation written in stone. And that's what people believed throughout the 20th century, without exaggeration. This is what people thought. There's no way out, and there's no way to get around that, really. Maybe a factor of 2 or so, but not really. You cannot get rid of it. And so not only they believed it, it also was a fact. So when I was a student, I will come back to that in a minute, in the late 80s in Heidelberg. So as Dr. Stucki just mentioned, I was asked to look into the development of laser scanning microscopy. It's called confocal, that's the technical term. And so this is the resolution that was possible to attain. So you see, it's showing actually some filaments in a cell, but it's very obvious that it's not nicely resolved. It's not very clear. Now, the development that I was awarded the prize for, it's called STED microscopy. So this is just a direct comparison. Showed for the first time that you can overcome this barrier, and that there is indeed viable physics, so to speak, or physics in this world, if you will, that will allow you to see much sharper. So, of course, this was a change because it changed the notion about the capabilities of the light microscope, and of course, this had a number of consequences, and I will talk about the consequences in a minute. Now, the consequences that it had for me personally, and it had consequences for me, actually were quite interesting ones, and if you will, pleasant ones. The first consequence it had for me that I had the privilege of meeting Scandinavian kings, and the first king that I happened to meet was King Harald V of Norway, because the Academy in Norway established a prize about 10 years back for the nanoscience called the Kafli Prize, and this is given out very similar to the Nobel Prize. It has about the same amount of money, and it comes with a medal, and the ceremony is like the Peace Prize ceremony, Nobel Prize. The Norwegians give out the Peace Prize, as you may know. And so it came with all the bells and whistles, and it was quite nice. And then I was surprised. I said, okay, now that's it. It won't get better. But I was mistaken, because I got a call basically telling me, okay, in a couple of weeks, on December 10, you will get the occasion of meeting the Norwegian king's cousin, King Gustav V of Sweden, And of course, in a nice celebration, of course, and he handed over this beautiful diploma and a medal, and this was followed by a nice banquet, I must say, a really nice one, with very good food and very nice company. And yeah. But you're not interested in the gossip, I know. So I'm not going to talk about what I talked with her that night. So I will come back to the science. So I will tell you now how this change was made and why I got involved into this and why it was me and not somebody else. Now you heard it already, but you may not have been aware of it. I was born actually in what is now the western part of Romania, but German ethnic. It's why German ethnic, because that part was, as you certainly know, of part of the Austrian-Hungarian Empire, and there were in that area, as in many other areas, were many minorities, including German minorities, and of course it was communist Romania. And I'd realized, like many others did actually, that this is perhaps not the best place to spend your life, and the opportunities you have in a communist country, of course, are not that good in the end. And so I convinced, at the age of 13, I convinced my parents to take advantage of our German background. West Germany had a very generous immigration program at that time, and to try to get out of the country. And after all kinds of problems, especially faced by my parents, I must say they were quite brave. We managed to get out of the country, cross the Iron Curtain, and move to this town in West Germany called Ludwigshafen am Rhein in 1978. Now you may ask, why did we end up here and not in Munich or, I don't know, Hamburg or Köln? Or it's very simple. My mother was very much scared that there would be a clash between East and West. And she said, we have to be west of the River Rhine. And so Ludwigshafen is a town west of the River Rhine, because she said the British and the Americans perhaps would not allow the Soviets to cross the Rhine. And so we have to be west of the Rhine. And so we ended up there, and I liked it. I thought it was a good decision because it was close to Heidelberg. And I knew, of course, that Heidelberg is a university town, and I wanted to study physics. I had a very education here, so the education, a very good education. The education in those days, I think in most Eastern Bloc countries, was very good, high top level. And so I could easily skip a grade here and get my high school leaving certificate. And so I wanted to study physics. And like most physics students in those days, I was attracted to basic physics. I wanted to become a theoretical physicist and I don't know, do important things there. But at the time, I had to make a decision to sign up with a professor to do my diploma work, or master's work, what it's called now, or my PhD work. This is what I looked like back then, believe it or not. I lost courage, actually, simply because I talked to other students and said, you should not do that. Because if you study theoretical physics, you do your PhD in theoretical physics, you won't get a job. Most people get unemployed, taxi drivers, and this kind of thing. And you should not do that. It made a lasting impression on me because, as you can imagine, my parents still had to struggle to settle, to establish themselves in the West. I was an only child, so I have to said to myself, I will have to support my parents in a way, and I should not do that. So I changed my mind, and I set up, actually, kind of reluctantly, with a professor that set up a startup company called Heidelberg Instruments. So, as a matter of fact, both Oliver Stucki, so the chairman actually, and I happened to end up in the same company for the same time. A small world, you see. I didn't know that he's here running Honeywell, but so it is. Anyway, I ended up there, and I was asked to test computer chips. So they developed laser scanning microscopes, and they had computer chips from IBM and Siemens, and my job was to to check out those computer chips if there is a production error. And now you can imagine if you want to do basic theoretical physics and this type of stuff and maybe unify the forces in nature, so theoretically, of course, and you do computer chip checks, something, quality checks, then you get bored. And not only that, frustrated. So I was totally frustrated. I was about to skip my PhD work, so it was horrible. I mean, I was happy. I was horrified by Monday morning and was happy to leave on Friday night. That went on for about a year, and I was just about to drop my thesis and do something else, or I don't know what. And then so I had two options actually, either to become very, very disappointed and perhaps miserable, depressed, or the other option was to, well, I thought, well, this is the 19th century physics. Maybe there's still something interesting or fundamental that can be done with a light microscope. And I thought about it, and I said to myself, well, the only cool problem that is left over, perhaps, is to break the diffraction barrier. Because that's something no one believes that would be possible, and it's in textbooks, and it has been there since the 19th century. So if I managed to do that, that would be really cool. That would be something, not just inspecting computer chips. And so, so I started thinking about the problem. So I went from the company, I went back home to the student dorm where I lived. So on the way back, I was thinking about how to break the diffraction barrier. So one night I said, okay, now I got the idea. Next morning I realized it's all nonsense, it won't work. And this went on like this for many, many, many months. But at some point I became convinced that there will be a way of doing it, and my reasoning was very simple. I figured that the diffraction barrier was actually found, so this law, this equation, was found in 1873. And in those days, it was 1888, 89. And so I realized 100 years had passed since then. So, so much physics was actually invented or discovered in the interim that there must be at least one physics phenomenon that would get me beyond the barrier. I just have to look for it. I have to screen textbooks for a phenomenon, and then I may find one. And so this is what I did. I started to screen textbooks, not reading papers or so, just textbooks, hoping to look into all kinds of phenomena and hopefully find one. And so at some point I put it down in writing. So this is a kind of technical saying here. So I was convinced that it wouldn't work just by improving the lenses. Objective lens doesn't make sense. It has to be either by, if you do fluorescence microscopy, by the features of the fluorophore, the states of the fluorophore, or by looking into modern so-called quantum optical phenomena, so that are phenomena that are quantum, because quantum mechanics came up in the 20th century, so if you look into quantum phenomena, it may work. Now, I couldn't find a job really, and so indeed I got unemployed. So at some point, and so I mean, if you were to check my CVs maybe 10 years back, I would not say I was unemployed. I said I was a freelance inventor, but I mean, now I can say it. I was unemployed, well, and then I tried to be a freelance inventor. But anyway, so I couldn't get a job, and I was fortunate because I met a person. He was Finnish, and that person said to me, "Oh, I know somebody who is a professor, and he's setting up. He just became a professor." And he set up a group here in this place that I had never heard of before. It's called Turku in Finland. And if you go there, you will get enough freedom. He will give you some money. In fact, he applied for a grant. He applied for a grant because I wasn't allowed to. And then you will get some money, and then you can work on it. You get a fellowship there. And this is how I ended up here in the summer of '93. In this place, and I tell you, in fall, it's really, the weather is really not nice, and it's getting very dark in winter. Summers are nice, but I got there in late summer, and so there was nothing to do but to read books, obviously, and so I took the book from Heidelberg, actually, and I checked out this book on a Saturday morning to find out whether I can find something interesting that could get me beyond the diffraction barrier. I opened this page, and I came across this technical term, which is called stimulated emission. Now, stimulated emission is a phenomenon that every physics student learns in the first year. And I'm sure many of you will know what stimulated emission is. And it instantly struck me, and I realized this is perhaps the way to go. This is such a phenomenon that can get me, for fluorescence microscopy, beyond the barrier. And that was just 6 or 8 weeks after I got there. And as a matter of fact, this won me the Nobel Prize. I'm explaining to you now the basics of this idea. So I was totally excited. There were no laptops in those days, so I went to the lab because I want to make some desktop simulations to see how it works. Now, this is the lens. This is the spot of light that has at least this size. It cannot be changed. It's clear, and also the fluorescence light has its own maximum or minimum size, so the diffraction blob. So that's something we cannot change. And all the molecules will be flooded by light. But, and that was my reasoning, if we manage to silence those molecules, so those molecules that are flooded by the green light, of course, if they are silenced, meaning that they are not capable of emitting fluorescent light, despite the fact that they are covered here by the green light, then we would see only the molecules from here, so only the yellow ones. Or if we silence all of them, but this one, of course, then we would see only the signal from that one. And then we can separate this molecule from the rest. And now, so the idea was to keep those molecules dark, despite the fact that they're flooded with green light. And now, guess what this phenomenon of stimulated emission does? I said the green light turns molecules on. It makes them fluorescent by exciting it from the ground state to the excited state. And this phenomenon of stimulated emission just does the opposite. Of course, it turns molecules off. So usually in fluorescence microscopy, molecules are just being turned on. You excite them, and then they emit light, and they come down by emitting a fluorescent photon. But we can, and that was the idea, just as we turn them on, we can also turn them off. And this phenomenon is called stimulated emission. By the way, a copy photon is produced that goes straight with the beam. We don't care about that. So we use a second beam of light that turns molecules off, and we turn them off only here. And as a result, only this molecule will be allowed to emit, and then we have one. And so this is the idea of what is called the STED microscope. Again, it has a lens, there is a sample, there's a detector, there is green light for turning molecules on. And of course, if you look at a sample from the top, these are the molecules, and you see the blob of light that is at least 200 nanometers in diameter. So this is the green light for turning molecules on, you see, turning on. But then we use a second beam of light that turns molecules off. And so we have this one. The wavelength is redshifted such that it cannot excite the molecule. So with the red light, it's impossible to excite molecules because the photon energy is not enough, it's too small. But according to basic laws of molecular physics, that red light will instantly push molecules back down to the ground state, and then they will decay here quickly and will not be re-excited by the same beam. So you have a way of turning molecules off optically. And so we turn molecules off. Of course, not all of them. It wouldn't make sense because then we don't see anything. So we will turn off only just a subset. But what I'm showing you here is, in order to turn them off, of course, it's clear that your intensity has to have a certain value. Okay? If this beam, this red beam, is weak, is very weak, then you will not be able to turn the molecules off, because if it's just, say, one photon every now and then coming, you don't turn it off. But if it has a certain intensity, like this intensity here, you can be sure that you will turn it off. So this is the probability of if you were turning the molecule off, if you increase the intensity of the red beam. So this is the probability of emitting, actually. And once the intensity here crosses this threshold, you have basically turned the molecule off. So what I'm saying by this, if the intensity of the red beam has a certain threshold, or is higher than that, of course, then you will have turned off the molecule no matter what the excitation light. And so what do? We convert this beam into a ring, and this can be done optically very easily by putting a piece of glass that has this helical phase ramp, and you will appreciate if two things are out of phase, opposite, so this is a phase ramp of 2 pi. If it's pi out of phase, then there is not a maximum of intensity in the center, there is a minimum, a 0 here in the center. So here in this donut, the intensity is 0 here, and it decreases up to here, and of course, this is the donut maximum, and then it decreases again. And so we can turn off molecules here, and you will say, okay, what is it good for? Because we may want to see only molecules from here and don't want to see those, because if you see those as well, we cannot separate this one from the rest. No problem. We make the beam, the red beam, strong enough, okay, so that even in the part where it is only 10% or 20% of its maximum, it is in absolute terms beyond the threshold. So you make it strong enough so that even here it is beyond the threshold, and that really turns off all the molecules in here, and only those are left over, okay? And in this way, of course, we can separate features or single out features that are at much smaller scales than what is given by the size of this green excitation spot or green illumination spot. And now by scanning those beams jointly over the sample, we can separate, of course, features that are very close to each other. You see? Okay, now this line here can be separated from that line because we force those molecules to be dark when these are emitting, and here those are forced to be dark when these ones are emitting. So this was the idea, actually, so in Finland. Just an idea. It was published as a theoretical paper in 1994, nobody cared. Really nobody cared, and it was very naive in those days. I thought, okay, if you come with an idea, and young man, I was 30, and then our people say, oh, wow, wonderful idea, and I was hoping to get a job. I mean, I'm not saying a professorship, I mean a job, and a bit of money to prove that this idea is right. It was a fundamental idea, after all, that's what I thought. But it was not like this. It was not like this. So nobody really believed in it. So I went around the States, applied for assistant professorships in the States, but if you don't have, say, the right pedigree, not from an Ivy League place, applications are ignored. And in Europe, the same, I applied to many places, and so I paid actually going to meetings from my own pocket because I wanted to convince them, and they smiled, nice, oh, very nice idea, but so it was very difficult to survive. So I survived with some fellowships. Actually, I made deals with local companies in Finland, so I gave them patents, and in return, they gave me money, $100,000. This was the maximum I got. And then with the $100,000, I could pay my own expenses and continue to get data or something, and the lab was not very well equipped. But the message that I have for you, I was not, say, miserable or unhappy during that time. I was much happier than during the time I did my PhD work, because I worked on a problem that I really wanted to work on. So I was really fascinated by what I was doing. I was the only one who looked into this resolution problem in the world. There was no one else. And so it felt quite lonely in that regard, but there is also some advantages to that. There is no stiff computation, and you really think the way about the problem you want, and it's new territory, so it was very exciting and fascinating. You know, it was only difficult to survive, so at some points I got frustrated and said, oh, I don't know if I will have money in 2 months from now or 3 months from now, but well. So I went to Oxford actually. Well, you may think because it's a good place. It's a good place, no doubt. I went there because I could get some money there for some time. But there was nothing to do there, honestly. And so I went back. But at some point, actually a group of scientists here at the Max Planck Institute in Göttingen, where I am now, they became aware of me. And they said, okay, we don't think, we're not sure if you're right or not, but at least we should give you the opportunity, because if we don't give you the opportunity, we won't know if you're right or not. So somebody we have to put it to a test. And so they gave me a job for 5 years with some money, and then I made, with my colleagues, the experiment, and then it turned out to work. So this is before, and this is after. And so these are certain protein complexes in a cell, and the comparison is quite obvious. Here you can see actually the 8-fold symmetry in this protein complex, and with the standard method you see nothing. And when I'm showing this, I'm usually saying that I really still like making this comparison. I mean, it's now in textbooks and so on, but but I clearly remember those days where this was thought totally crazy and nuts and exaggerating. Now, there is interesting applications, by the way, in the life sciences. So this is a colleague in Heidelberg I collaborated with, and these are particles from HIV, and there's a certain protein on that particles. It's called ENF, and so those are very important because they are responsible for connecting of the HIV particle to the next cell and infecting that cell. And normally you don't see anything here, so it's very clear because the virus is much smaller than the resolution barrier. So it's not possible to see the structure or the distribution of those proteins, but here you can see it quite nicely. And so here, to cut a long message short, because you're not interested in the biology, you learn something about the distribution of these proteins that are very important for HIV particles, and learn something about their role in infecting the next cell. Or it's possible to see so-called synaptic vesicles in living cells. So this is the standard resolution, and this is now the high resolution. You see the moving, because as I said, one of the strengths of fluorescence microscopy is that you can see living cells in action, or molecules or molecular entities. And this is live cell imaging at the extreme. This is an anesthetized mouse, and so the skull of the mouse was open, and some of its neurons had some fluorescent molecules in them. You can make the mouse genetically modified such that this is the case. So this is the rest of the brain, and this is a certain neuron. And now one can clearly see those so-called synaptic these features. So these are so-called spines, and this is the synapse actually. So this is the postsynaptic side. So this is where the neuron receives its message from the adjacent neuron that you cannot see right now, simply because it's not highlighted. But not only that, you can also see it, so to speak, in action. So this recording showed that the brain is in constant action, not only chemically, but also mechanically. There are subtle changes going on, and here they are highlighted again. And you need a high resolution in order to see these subtle changes. And so this is actually quite interesting, and it shows the advancements that are made as a result of the high resolution. Now, this is the first type of this data, so this is why I say 2012. By now it's much better, because science progresses and technology improves and so on, but this is the first of its kind. And of course you can also get three-dimensional data, because it's possible to focus into the cell and get from information from within. Now, coming towards the end, I would like to just make a few remarks about development. You should not underestimate technological development. So initially, in 2000, that microscope still looked like this. So it was already functional at that time, but it was very complicated. And now, of course, you can buy it from commercial vendors. So these are two of them, and there's even one of them in action, actually. If you go down the hall, I was surprised to learn that this morning. It looks like this, so it's very compact, smaller than a shoebox size, as you will see. And one of the guys who developed it are out there. Is one of the best students I've ever had. And this picture was actually taken with such a commercial system from that spin-off from my group, and I'm proud of it because it made it onto the official poster of the 2014 Nobel Prize. And this poster you can get from the Nobel Foundation. You just write them an email and they send it to you, or I can send it to you too if you want, even as a PDF, if you're interested for some reason. And here they explain actually, on the Nobel poster, they explain the nature of the prize and what they awarded the prize for, the Nobel Commission. And so here it explained this microscope that I'm standing for, the STAT microscope. with the green turning on beam and the red turning off beam. And so this was the first microscope or type of microscope that crossed the threshold of resolution. A couple of years later, American colleagues demonstrated a related method that had a number of advantages, like they turned molecules on individually, on and off, which has some advantages and also was quite well received. And so the Nobel Commission decided that I will have the honor of sharing the prize with these two gentlemen from Stanford and from Howard Hughes Medical Institute in Geneva Farm. And so that was the state of the art in 2014 when we were awarded the prize. So it was clear that in principle, both methods, both this method STAT and the other one, it's called PALM by the way, can attain a spatial resolution that is about a nanometer, so molecular size, but in practice, they didn't. They just crossed the threshold, these methods, to be fair, but did not attain the 1 nanometer resolution which could have been attained in principle. But of course, a factor of 10 is a lot. This is why the Nobel Prize was awarded. And so I felt, after having won the prize, we should not just cross the threshold, we finish off this story and really should get down to the 1 nanometer resolution that was conceptually possible. So, so I went back to Göttingen and said, okay, we have to attain the ultimate limit and do something. And so I'm briefly mentioning what happened after the Nobel. So we introduced a new type of microscope, it's called min-flux, that really attained for the first time the 1 nanometer resolution. So this is, so to speak, new science, if you like. And so what was the basic idea? So I had realized that to two methods, like the one that I introduced first and the one that were introduced by the American colleagues, have particular strengths. And if you combine those particular strengths, without going too much into detail, in a non-trivial way, in an unexpected way, then you will kind of multiply the tenfold increased spatial resolution that is provided by this one and the tenfold increased spatial resolution provided by that one. And so you end up with a new scheme that really allows you to see or distinguish molecules that are at true molecular distances. So the size of a molecule is 1, 2, 3 nanometers or so, and so this is 11 nanometers is of course at a molecular distance, and now you can really tell them apart. So with this new method, it's called min-flux, we can see the molecules at closest, and the resolution is of the order of a nanometer. Now we have really attained the limits, and so the old method, or the one that was awarded the prize, doesn't get it. So it still looks like this, and so we made a significant step, or well, I believe it's the ultimate step beyond the diffraction barrier. And not only that, it also allows you to see the trajectory, the movement of molecules with very high spatial precision and high temporal spatial resolution. And I think this will be interesting for understanding what's going on in a cell, in a living cell, at a molecular level. And I'm quite hopeful that this will contribute also to understanding not only the physiology of the cell, but also diseases. Because in order to understand what diseases, we have to find out what happens on the molecular scale. Because after all, and this has been known since the mid-19th century and has not been changed, a disease is ultimately rooted in the cell. So you can boil down any disease to a malfunction in the cell. And so, I'm summing up, the idea behind overcoming the diffraction barrier is very simple. You turn molecules on and off, and it's not, again, it's not anymore about making nice lenses as in the 20th century. It's all about turning molecules on and off, so very much boils down to making molecules that can be turned on and off. So it has become a chemistry problem in a way, and of course this can be extended also to other signals that can be turned on and off, like non-absorbing or not scattering or whatever. So there's more science to it. I'm just saying that, and I didn't speak about that, but it's very easy to show that you can expand, of course, this equation by putting in the square root factor. And this is quite good news because, as you will appreciate, if this number gets very large, like 10, 100, and so on, D gets very small, and as we've seen, you get it basically now down to the molecular scale. And of course, we can image things at much higher spatial resolution. But in the end, as I said, it boils down to one thing. The reason why we can separate this fiber from the other one here, but not here, is at the time the molecules here were emitting, they were on, those were off, and at the time those were on, those were off. So simple. So in the end, big problems usually are solved with very simple solutions. So my suggestion is, if you try to come up with something new, come up with something simple and make it as simple as you can. And once, and if you have not reached the utmost simplicity, you have not done your job. Okay, with that, I'm acknowledging the people who have contributed to this development. Many of them have become professors or set up companies and so on. And some of them are still staying in my lab. So I did not just work by myself. But of course, it's always important to have somebody who believes in it. And with that, I'm thanking them, and I'm thanking you for listening so patiently. Thank you very much.